So thank you for coming our talk. So my name is Masa. I'm a researcher at NEC, and he's my co-speaker, Yohei. He's a research fellow of NEC. So today, we are talking about big data heterogeneous mixture learning on Spark. So first, Ryohei starts this talk.
Okay, so today we're going to talk about predictive analytics. So NEC is currently offering a lot of predictive analytics services to our global client using our own machine learning technology that we call heterogeneous mixture learning, or simply HML. And recently, we are receiving quite a lot of needs for analyzing very big data using HML. So this talk explained how we leverage the power of HML using Spark for analyzing that big data, and shared 3 key technical points that we addressed to maximize the performance of HML algorithm on Spark: data shuffling, map-reduced synchronization, and matrix computation. So these points are applicable not only for HML, but also design of any or general distributed machine learning algorithms. So I hope you will take away some of points for designing your own distributed machine learning algorithm. And in addition to 3 key technical points, we are going to explain 2 business use cases. One is data science application for banking customer. More specifically, demand forecasting of cash balance for ATMs, a lot of ATMs. And this is very important for maximizing operational efficiency and profitability of ATM. Another use case is on-premise deployment. So we know that kind of one of big trend of this Hadoop community is shifting to cloud side. And of course, NEC is working on that area. But a lot of our customers, particularly for the industrial leaders, big customer, still want on-premise data, high scalable data analytics platform because of data security issue, because of regulation or legal perspective, or simply they cannot invest a lot of money for shifting environment from current on-premise environment to cloud. So to meet those needs, NEC is offering kind of appliance data analytics platform. Everything is inside in a very compact, dense servers. That is micro-modular server. Actually, in 2U space, it contains 42 servers inside. And in this server, everything need for data analysis like Hortonworks, HDP, Spark, HML, Jupyter Notebook for data scientists, Python, and the machine learning libraries are integrated. So I hope through this presentation, I hope you understand what is HML and how we maximize the performance of HML on Spark and our capability in this predictive analytics service area. So let me start from what is HML. So these are a part of use cases that we are offering in the market. And for example, energy water operation management, like predicting demand of the water in many locations, and then optimize the creation or distribution plan. Or for retail customer, like predicting how many sandwiches will be sold in next 24 hours in store, then we can optimize the inventory or price to maximize the revenue or profit of the store. Driver risk assessment, preventive maintenance, these are very exciting ongoing projects in Singapore, and actually I personally working on these 2 projects. Churn retention are very important use case for NEC and applicable to the very various industries. So NEC is offering this type of predictive analytics services using only single machine learning algorithm, that is HML. So HML that we have invented derives accurate and transparent predictive formulas. Suppose we have the very data collected from very heterogeneous data sources. Then HML explores massive patterns or formulas, and then combine multiple formulas to make the high accurate prediction. So let me give you a more concrete example of how the HML model works. You can see our data segment. This is an example of health risk prediction. And you can see the data segment, like a female or short man and a tall man. And then for female, weight, drink tea, coffee, or sports, these are the key risk factors. But the different segment, different risk factors. So by switching the optimal formula for segment, HML can produce a very highly accurate prediction. And one very unique feature of HML is this transparency of predictive model. So deep learning is currently a very hot topic in market or in industry. And we have our own deep learning technology. And it's very good for image recognition, natural language processing, information retrieval. But actually, our enterprise customer or healthcare industry, public industry, they don't like black box prediction. So they need a reason of prediction. Why machine make this prediction? So this is why most of our customers choose HML rather than deep learning, even if deep learning is slightly more accurate. So if you are a data scientist, you might think the model HML produce is nothing but the data scientists usually make in manual way. Like for retail case, partitioning data for weekday and weekend or sunny day, rainy day, and the daytime, nighttime, then apply the linear regression and see the fitting score. Then if it's not good, then change the data segment again or put the new features and looking at the result again and this trial and error. So the beauty of HML is to automate this process, and HML, just putting data, HML find the best number of data segment and the number of features or coefficient of features. Everything is automatically determined based on the Bayesian learning theory. So let me explain a bit more detail about how the HML algorithm works. So there are two key procedures. One is data segmentation, and another is feature selection. So data segmentation, HML find the best segment. For example, in this case, locational feature and the weather feature is the key to find a segment. Segment is kind of a change point of the data regression. So between here and here, data regression change. And the HML identifies this case, 3 data segment. And this number is automatically determined by algorithm. And in feature selection step, like the healthcare risk prediction case, different segments usually have the different key features or different key factors. And even the number of factors are different. So HML first find the number of features and which features and determine the coefficient of these features. And by iterating these steps and until convergence, HML find the optimal formula, predictive formula. So as explained, we have already delivered a lot of predictive analytics services in the industry using HML. And recently, we are receiving big needs for analyzing big data. So for example, churn retention case, suppose our customer has a service with 5 million subscribers, and we have 12 months training histories. Then we have the 60 million training samples. And the 60 million is not that big number, but actually it doesn't fit on the memory of the single machine anymore. And we need some distribution mechanism. And as you can easily imagine, this number can be easily bigger, like more subscribers or longer training history. Retail case. Suppose our retail customer, franchise customer, has 1,000 stores, and they have product or they want to build a predictive model for 100 items in store. Then we have to build a 100,000 prediction model. So in this case, the number of prediction model is very big. So to meet this kind of needs for learning HML model for this big data, so we combine HML and Spark, and that is distributed HML algorithm. And Masa is going to explain the details of this distributed HML on Spark.
Okay, so from now, I'll explain the distributed HML on Spark. First, the reason why we choose Spark is Spark's in-memory architecture is very suitable for running machine learning algorithms fast. So on Spark, with once data loading from the disk, all execution of machine learning algorithms is done in memory without slow disk accesses. Yeah, this is a Hadoop summit, so you know the Hadoop. Hadoop is one of similar distributed computing systems to Spark. But unfortunately, Hadoop is not suitable for running machine learning algorithms because it requires multiple slow disk accesses during its execution of machine learning algorithms. And powered by Spark, we can treat unlimited scale of training data. So Spark is a MapReduce-based scale-out architecture in common with Hadoop. So we can increase the memory space and CPU power by just adding the executor servers to the cluster. Here, this figure illustrates the architecture of distributed HML engine. So you, data scientists, can use the Python interface of distributed HML via the Jupyter Notebook. And that Python interface invokes the core of distributed HML implemented in Scala. And the core runs on the middleware stack, including Spark, Yarn, and HDFS. So internally, the core calls the high-speed matrix computation libraries like Breeze and Blast to accelerate the execution of machine learning algorithms. And after the execution, the core returns the generated HML model to the data scientist via the Python interface. Okay, so now let me ask one question to you. Do you think any design and implementation of machine learning algorithms can run fast on Spark? It's unfortunately not true. So to run the machine learning algorithm fast on Spark, we must address 3 technical key points. The first one is data shuffling, and the second one is MapReduce synchronization, and the third one is matrix computation. So in this talk, I'll explain how distributed HML addresses these 3 technical key points one by one. So the first one is data shuffling. Avoiding data shuffling is very important to run the machine learning algorithm fast on Spark. So even if Spark diminishes the slow disk accesses, heavy network communications must seriously degrade the execution performance because the network access is very slower than the CPU computation and the memory accesses. The important point of this discussion is the size of training data. So it usually becomes a big size, so more than terabytes. So if we design the machine learning algorithm so that it requires to refer all training data during its execution, so each executor must shuffle the training data between the executors and driver. So it produces much network communication, and it seriously degrade the execution performance. On the other hand, the size of HMM model is very smaller than the size of training data. It's usually from the 10 kilobytes to 10 megabytes. So from this observation, we designed the distributed HML so that it merges the locally learned HML model on executors with locally partitioned training data into one fixed and consistent model on the driver. So this design avoids the data shuffling of training data, and it can run the algorithm very fast on Spark. So let's see the execution flow of distributed HML based on that design. So at the first step, data segmentation phase, so executors build a rule-based tree from their local training data in parallel. Because of the difference of the partition training data on executors, so the trees might be different from each other. Then, so driver merges the trees, and it fixes one consistent tree on the driver. Then, so the driver broadcasts a merged tree to executors. At this phase, so one tree is fixed on all driver and executors. Then, so go to the next step, feature selection phase. So executors perform the feature selection with their local data in parallel. So in common with the data segmentation phase, the selected features might be different from each other. So the driver merges the results of feature selection, and it fixes one set of selected features. Then, so the driver broadcasts the merged results of feature selection to executors. So according to this procedure, so distributed HML continues the cycle of HML algorithms step by step. So now let me explain the first point again. So the first technical key point is the data shuffling. And to avoid the data shuffling of training data, so distributed HML merges the locally learned HML model on executors into one fixed and consistent model on the driver. Then, so it avoids significantly reduces the network communications, and it can run fast on Spark. Okay, so let's move on to the second point. So second technical key point is the MapReduce synchronization. So as you may know, Spark is a MapReduce-based synchronized architecture. So on such a synchronized architecture, waiting time for slow executors is very can seriously degrade the CPU utilization of the cluster, and it finally makes the execution time longer and longer. So particularly, such a waiting for slow executors seriously degrades the execution performance of machine learning algorithms, because the machine learning algorithm is a CPU-heavy computation workload. So let me share one example of such a case. So suppose that we designed the distributed HML so that each executor optimizes one predictive formula in parallel. Then, so the execution time significantly varies, and the waiting time for slow executors increases. This is because the optimization time varies depending on the predictive formulas. So to balance the computational effort for each executor, we designed the distributed HML so that each executor optimizes all predictive formulas with equally divided training data. Then, so the execution time is balanced, and the waiting time for slow executor is significantly reduced. And finally, the completion time is reduced. So now, let me explain the second point again. So the second technical key point is MapReduce-based synchronization. So it's important to reduce the waiting time for slow executors to increase the CPU utilization of the cluster. So we designed the distributed HML so that to balance the computational effort for each executors. Then, so the completion time is significantly reduced. Okay, so let's move on to the third one. So third technical key point is matrix computation. Machine learning algorithm consists of many matrix computations. So distributed HML also performs many matrix computations, including basic matrix computation, matrix inversion, and combinatorial optimization. So it's a bit, to accelerate the machine learning algorithm execution, it's very important to accelerate the matrix computations. And it's a very good way to use high-speed native matrix computation libraries like Breeze and BLAS. But however, if we design the RDD very straightforward and naive, so there is a heavy computation overhead happen to call the matrix computation libraries. So let me share one example for such a case. So suppose that we designed RDD so that each element contains only one training sample. Then, so to call the matrix computation libraries, there are many iterator accesses and matrix object creations happened in map partition RDD operation. So this calculation is very wasteful, and they produce a much computational overhead. So to avoid such a wasteful overhead, we designed the RDD of distributed HML so that each element contains one matrix object directly with 10,000 or 100,000 training samples. Then, so the distributed HML can directly call the matrix computation libraries without iterator accesses and additional matrix object creations. So it reduces the overhead of the calling the matrix computation libraries. So let me explain the third point again. So the third technical key point is matrix computation. So to accelerate the matrix computations of the machine learning algorithm, we must be careful to design RDD for the algorithm. It's a very good. You might see that this is a very trivial technique, but it's a very important and fundamental technical issue to run the machine learning algorithm first on Spark. So I'll explain this one here. Okay, so by the way, let me share one additional performance issue of the machine learning algorithm on Spark. So through the development of distributed HML on Spark, we noticed that the execution performance is seriously degraded by the long-chained RDD operations. So because the distributed HML is a cycle-based algorithm, there are many RDD operations happen in the execution, and they are in a long chain. So if unfortunately the intermediate results of the RDD operations are flushed by the garbage collection, then so the next step of the distributed HML has to recalculate the flushed results back to the one available on the memory. So these are very wasteful computation overhead. So to avoid such a wasteful recalculation overhead, so we improve the implementation of distributed HML so that it cuts the long chain operations periodically by the checkpoint API call. Then, so even if the intermediate results are flushed from the memory by the garbage collection, distributed HML can continue its execution from the saved state of RDD by the checkpoint API call. So, but however, we don't think it's the best solution to this problem because the checkpoint API issue is disk accesses. So we are still exploring a more better solution to this issue. So if you have any good ideas, please share them with us and let's discuss it. Okay. All right, so let's move on to the benchmark performance evaluations. So our evaluations consist of two parts. The first part of evaluations compares the prediction error with the algorithms of Spark MLlib. In this comparison, we choose three algorithms of Spark MLlib: logistic regression, decision tree, and random forests. And for this comparison, we prepared 4 open datasets from UCI machine learning repository. Okay, so these experimental results demonstrated that distributed HML achieved a low error competitive to the 3 algorithms, especially a complex model like random forests. The second evaluation compared the performance scalability of with the algorithms of Spark MLlib. So these figures compare the normalized processing time between the algorithms and the number of CPU cores. So these experimental results demonstrated that the performance scalability of distributed HML is competitive with that of Spark MLlib implementations. Especially so, distributed HML achieved the performance and overcomes the performance scalability of random forest. Random forest is a very good implementation of the Spark MLlib. But yeah, distributed HML is competitive to that one. Okay, so let's move on to the evaluation in real use case. To demonstrate the value of distributed HML in real use case, we performed one case study of the ATM cache balance prediction with real data. So let me explain the abstract of this case here. So suppose that each ATM stocks $50,000 US. Then, so if we have 20,000 ATMs, so the total size of stock becomes $1 billion US. So it's a very big cash. So even if we reduce the stock by only 10%, so we can invest 100 million US dollars for other purposes. So it's a very big chance, opportunity to earn more revenue for the customers. But if we reduce the stock too much, the risk of out of stock increases and the customer satisfaction must be degraded. So in this case, high prediction accuracy is very important, and it's also important to keep the accuracy. So in this evaluation, first we evaluate the training speed of distributed HML. So distributed HML completed its execution in only 2 hours. It marks 110 times speed up from the original or serial HML. So this means that distributed HML can update its HML model day by day, and it can provide a high accurate HML model day by day with the latest updated training data. So actually, in this case, we can improve the execution performance of the serial HTML by dividing the training data into small parts. But unfortunately, it must degrade the prediction accuracy because generally. On the other hand, distributed HTML can use the all training data during the execution. So finally, distributed HTML marked 17% lower average prediction error compared with serial HTML. So this means distributed HTML can provide a more accurate model to the customers. So now, okay, so by the way, how to deliver the data analytics platforms to the customers is a very big important topic for the solution vendor. So here, so to quickly deliver the HTML data analytics platforms to many enterprise companies, we are developing an all-in-one appliance for HTML data analytics using our unique server named Micromodular Server. So here, let me introduce its concept. So as you may know, so cloud service provides a very quick start of distributed, data analytics. So on the cloud services, data scientists can start their data analytics with low operation effort for middleware, including Spark, Yarn, and HDFS. And they can start with no space and power consumption cost and no installation effort. But however, cloud service also has 3 disadvantages for big data analytics. So first, it costs a high pay-for-use charge for big data analytics. Second, it requires a complicated software design for your data analytics applications because your application must run in an unreliable computing environment like spot instances. Third, cloud service still has a data leakage risk because you must upload your confidential data to the cloud services via internet. On the other hand, on-premises deployment has reverse advantages and disadvantages of the cloud services. So it's very difficult to launch and operate a Spark cluster from scratch, and the cost of the installation, operation, and space and power consumption are generally high. So to break out the dilemma between the cloud services and on-premises deployment, we are developing an all-in-one data analytics appliance for the HTML data analytics. So the concept of our HTML data analytics appliance is quick and analytics. So on our appliance, data scientists can start their data analytics quickly, powered by the all-in-one software stack, including HTML data analytics engine, Jupyter Notebook, Python interpreter, Apache Spark, and HDP. So our appliance combines the advantages of both cloud services and on-premises deployment. Especially, it reduces the data leakage risk of the cloud services. So a significant feature of our appliance is its hardware infrastructure named Micromodular Server. So Micromodular Server is a kind of mini cluster which employs 41 server nodes internally with 328 CPU cores, 1.3 terabytes memory, and 5 terabytes SSD storage in only 2U space. So Micromodular Server reduces your cost of installation and operation, and it saves space and power consumption cost. In addition, our appliance achieved a more better cost performance compared with the standard cluster. So micromodular server, in our speed test, micromodular server marked a 1.6 times speed up from the standard cluster in the ATM cache balance prediction case. So this means on our appliance, data scientists can conduct more experiments to develop the data analytics pipelines for your businesses using HML technology. And furthermore, we've released more powerful succession hardware named Scalable Modular Server for a larger scale of big data analytics. So Scalable Modular Server improved the CPU power by 2.3 times. It increases the memory space by 1.7 times, and the storage space, SSD storage space by 3.3 times. So now we are integrating the HML data analytics software stack with a Scalable Modular Server. So stay tuned. Okay, so finally, let me summarize our talk. So in this presentation, we introduced HML data analytics of NEC. And so HML it has already achieved many successes of real use cases. And for demand of big data analytics, we've developed distributed HML on the Spark. And distributed HML addresses three technical key points to run the machine learning algorithm first on Spark: data shuffling, map-reduce synchronization, and matrix computation. And so our evaluation with real data demonstrated that distributed HML can provide a high predictive, high accurate HML model day by day. And so to quickly deliver our data analytics appliance to many customers, so we are developing all-in-one appliance using our unique server, micromodular server, and scalable modular server. So now, distributed HML is ready to use, and we are exploring more real use cases in enterprise businesses for the big data analytics. So if you are interested in the distributed HML technology, and you have a big data, so please feel free to contact us. So thank you. So we have 2 minutes for the questions. So do you have any question? You?
So are there any use cases that have been done around financial, like investment, like portfolio optimization, investment risk, futuristic risk?
Yeah, actually, we are currently working with financial customers, and yeah, they have a lot of key use cases. Like, yeah, when you say financial services, like a banking or credit card or different. Okay, so in that case, like for example, risk scoring type of application, like we have done like a risk scoring for loan. And you know, just the assess the risk of commercial customer who need a loan for the bank, something like that. And currently, we are trying to extend this use case for more like a churn or customer relation management area, not a risk area, but more like a customer relation.
Anything on portfolio optimization?
Portfolio optimization, actually, we have the portfolio optimization use case, but not with HML, but it's more like we have a very nice kind of optimization OR type of technology, and we have the like a robust optimization type of thing, and that we are using for portfolio optimization, not the machine learning.
I'm interested in these three techniques, data shuffling and the rapid user synchronization. Are there any best practices, or have you applied these principles in other domains?
Maybe maybe the question, repeat the question. Question is if there's any other use cases that we apply to these three key technical points.
Exactly these things. Do you have applied them to other domains? Are there any best practices that you can extract?
I think this is common for the Spark applications. Like I guess so Spark SQL, so data manipulation in the Spark SQL is also they must address data shuffling issue and the synchronization issue. So yeah, Spark SQL doesn't contain the matrix computation, but the first 2 points is very important.
Yeah, I think his point is very important for Spark SQL. So for machine learning use case, we generate, for example, thousands of features using Spark SQL. In that case, like data, how we distribute the data and how we design the scheduling of Spark SQL is related to data shuffling issue. And also checkpointing issue. That is also important because executing a lot of SQL queries could cause such issue potentially.
So
sorry, we can have the offline discussion because time is up.
Thank you.